Hello everyone, and welcome back to Introduction to Number Theory. This time I would like to discuss Diophantine equation with a linear Diophantine equation with three unknowns, x, y, and z. We'll discuss the general case ax plus by plus cz equal to some integer number d, for instance. And I would like to show that if a, b, and c are mutually prime, which means that the greatest common divisor of all three of these coefficients is equal to 1, then there exists an integer solution of this equation. An integer solution of the equation. We already know when a linear Diophantine equation with two unknowns has a solution. So let's transform this equation into a linear equation with two unknowns by transferring cz to the right-hand side. We obtain ax plus by should be equal to d minus cz. Here we refer to z as a parameter of an equation. We know that this equation will have a solution if and only if d minus cz is divisible by the greatest common divisor of a and b. And notice that the greatest common divisor of a and b is not necessarily equal to 1, because we only know that the greatest common divisor of all three numbers is equal to 1. One may think, well, if the greatest common divisor of three numbers is equal to 1, then perhaps there should be a pair of these numbers which are mutually prime. But this is not necessarily so. Simply consider such numbers as 10, 15, and 6. These are three numbers. Two of them are mutually prime, but all three, their greatest common divisor is equal to 1. So d minus cz should be divisible by the greatest common divisor of a and b. Well, what does this mean? This means that there should be an integer x, y, z, t. There should be an integer t such that d minus cz is equal to ab, the greatest common divisor, multiplied by t. Well, this equality here is actually just another equation. Let's write it in the standard form. The greatest common divisor of a and b multiplied by t, where t is one of the unknowns, plus cz should be equal to d. And in order for this equation to have an integer solution, well, its unknowns are t and z. So in order for t and z to exist, d should be divisible by the greatest common divisor of the first coefficient and the second coefficient. But of course, the greatest common divisor of a and b and c is precisely the greatest common divisor of a, b, and c, and we know that according to our initial conditions it is equal to 1. So this holds. D is indeed divisible by the greatest common divisor. This equation has an integer solution. Therefore, Therefore, there exists an integer z such that d minus cz is divisible by the greatest common divisor of a and b. Therefore, this equation has an integer solution, and we can say that there exists integer x and y, and this finishes our proof that indeed, if the greatest common divisor of a, b, and c is equal to 1, then there exist x, y, and z satisfying this condition.